All right, so tonight we're talking about exceptions. Now, again, if you're an undergraduate, some of this content has appeared a little bit more prevalently in the undergraduate course that I used to spend a lot of time running, 1531. Probably about 20 or 30% of it. So apologies for the repetition. There is a little bit of like general computer science theory here, as well as C++ specific stuff. So firstly, when it comes to exceptions, sometimes our programs deal with unexpected problems during runtime. Now, we kind of chatted about this a little bit early on in the term, which was like errors can happen at compile time or they can happen later. There are some things that we just don't know if will go wrong during runtime. And a really good example for you is maybe it's not the best example, but if you think about assignment 1, when you had to load in the file english.txt, you can compile that file all you want with english.txt hard coded in, but it's not actually until that file is opened at runtime that you know what the contents are. You could compile a program fine, and then someone could go and remove everything from english.txt and the program could fail during runtime. So this is important because there are certain errors, many errors, where you just can't be sure that, at compile time it's going to go okay. And because of that, we need good, graceful, elegant ways to deal with these errors coming up. And these are the kind of topics that we're gonna chat through during it. So firstly, let's explore an example. Here's a piece of code. You enter -1, it prints out enter -1 to quit. We create a vector of 4 items. You ask the person enter an index, 0, 1, 2, or 3 in this case. And then what it does is, sorry, maybe I've misunderstood it. Standard CN print index, yeah, it just reads in one index from standard CN. It's a type int, so it will get cast to an int. And if it's in that list, it will print it out. If you enter -1, it'll quit the loop. Let's just play around with the program, right? We don't need to kind of describe it verbally too much. So I'm in this week's folder. Do I have to set up CMake? I do. CMake-b build. Let's go inside the build folder here. Don't worry about those warnings again. Just give that a sec. Cool. Okay, hit make. Oops. I think we might already have a program that's a little buggy. Let me just get rid of that one for now. CMake lists. We'll just start with these files. Nope, we've still got problems. This is very strange. Auto type specifies a C++11 extension. Yes, I know that. It's very weird. Maybe I've got something wrong with the compilation here. Have I got a problem in my CMake lists? I don't think this would be the problem, but let's try it out. Nope. This is very strange. I have a feeling that for some reason it isn't liking this. Let me try one more thing out. Yeah, something's definitely going wrong with the C++ version. I'm not sure what though. Yeah, it wouldn't exactly. But we haven't, that's not the strange part. The strange part is that this is the same kind of thing we've been doing every week in the same folder. That's what's particularly strange about it. Well, like if I just try and think about this for a sec, we did lecture 4.1, right, with some of these other examples like overload assignment. So if I go and take our exception 1 and I go put it in overload assignment, then we go back to 4.1, we go to build, make overload assignment. So that worked. But if I have the exact same code here, 5.2, oops, cd, make cd build, make exception 1. Oh, of course it worked because I fixed the bloody problem. Silly me. Very interesting. I don't know. Doesn't really matter because we can kind of get around it. That's okay. Very weird. I'm still mostly perplexed though by the fact that this is not working because it should. Let me try remaking some stuff. I don't know. No project command was present. The top level CMake list. Maybe that's part of the problem. I'm not sure. Oh, did I really do what I think I've done? Maybe. Let's see. Oh, I have. Oh no. I just totally has someone beat me to it? Nope. Okay. So let me quickly explain. This term I've had to do a little bit of teaching for Comp 1531. And what we do with that is we actually have our own build system in each folder. And I've been lecturing that for the last week. And what that means in those courses is you go into the folder and then you do like the install there. And that just totally took my head out of the fact that in 6771, we've been doing all of our builds from the same build folder. So in this particular case, this exception 1 file will work now because I'm building it from the right file, which kind of makes sense because particularly those first errors you get where it was saying like, we don't think it's C++11, that should have been more of a red flag because, or basically what CMake is trying to do in that instance is build a CMake list configuration from just these files. So it's going to fall back to a whole bunch of defaults, which will include C++98, for instance. But when we actually created it from the right folder, which was in here, we will get things that work for us. So anyway, I built exception 1, very interesting. Build exception 1, and then we'll make exception 1, right, which is 5.1 exception 1. And that program over here will ask us to, I'll just make it really visible, enter an index. So I enter 0, cool. I enter 1, I enter 2, I enter 3, 2, 1, I enter 4, and the program crashes. And if I enter -1, it exits as well. So the -1 is like a graceful exit here because we do a break. Whereas if I type in a number that is 4 or above, what happens is that it actually fails on this line here, where we take our print index, which was an int, we static cast it to an unsigned int, and then we call .at on it. And what you'll notice here is that the C++ compiler says terminating due to uncaught exception of type std out of range vector. So basically what we're dealing with in this case is that the vector realized there was a problem, got very upset, did something called throwing an exception, and then it crashed the program. By contrast, and you remember this from our operator overloading lecture, if I change this from .at to the brackets and I enter 3, it works, but if I enter 4, oops, sorry, I gotta make it first. It's gonna try and make all of them now. Oh, literally all of them, sorry. Make exception 1. If I try and run this now, enter an index 3 to an index 4, here's where things get pretty interesting. And because we kind of talked about how the difference between at and subscript was that at had a small exception check in it, which meant that it actually explicitly checked if the bounds were okay before it returned it. And if it wasn't okay, it threw an exception. It basically threw an error. Whereas the subscript does not do that. And that's actually kind of scary in this case, because what's happening is the subscript operator is literally just saying, hey, yeah, get me items 10. And because we're dealing with a language that's like C, what that will mean is that it's simply going to actually try and access that exact memory address. So we're comfortably overflowing right now. But at some point, 20, 30, 40, 50, 100, 200, 500, 1,000, 10,000, maybe it's just, yeah, at some point it just crashed. Maybe that was because int max or something. I'm not sure. Normally I get these to segfault a bit quicker. I think that one's just not taking in the input because I can't actually cast it to an int. I think the number's too big. There you go. There's a segfault. So at some point here, items had a particular memory address, and then we asked for the 345th million element past that, and we got a segmentation fault. Whereas naturally, if this was the .at, we get a different kind of thing. If it was .at, it would just, again, give us that exception. Oops, sorry. Gotta make it. See what happens? I do literally 2 lectures on JavaScript, and my brain completely forgets how compiled languages work. So we got a 4 there. Crash, totally fine. So that's us exploring it a little bit. However, if we were to use exceptions instead, i.e. we take this code we see up on the screen here and I change it to add a little bit more information, what we can do now is listen to that exception that is thrown by standard vector and do something with it. So in this particular case, what happens is that this item.resize doesn't need to be there. I asked for the vector, whatever, but I've wrapped it in the try-catch block. Now you should know the try-catch block from other courses in Python. It's try except, you've probably seen that before, is I try to access it. However, I listen for the std out of range error here. And if I hear it, I catch it. And if there's any other kind of errors that happen, that's what that other line was for, which I'll leave here but comment out, we do something else. So in this particular case, I'll show you what happens, is that I have my program. I'm going to make exception 2 now, and then I'm going to run exception 2, and I'll do the same thing, 0, 1, 2, 3, 3, 2, 1, 0. However, I will type in 4, and it prints index out of bounds. So this is important because what's happened in this case is that rather than this kind of generic system error, I've actually kind of caught that exception and done something with it. I could do anything I want here. It doesn't have to be an error message. It could be me printing out, painting my fingernails or something like that. This would be, there you go. So it's just handling that. So you kind of got to imagine that, when you call a particular function, the function might throw an exception and yells out, someone then catches it, does something with it. Fairly straightforward there. Let's take a step back and unpack it, because I like to start with a demo, even though there's a lot of details floating around there, just so you can all get at least a practical sense of what we're dealing with. So the reason we call things exceptions is because they are ways of dealing with what we would consider to be exceptional circumstances, or maybe a better way to explain it is a runtime anomaly whilst you're running your program, because an anomaly is something that is unexpected, and runtime is what happens when you run your code, not compile time. Again, very, very different. So exception handling in C++, C++ does detect runtime errors and raises appropriate exceptions. Often that's kind of built by the people who edit the libraries. And I think what is one of the most important things about exceptions conceptually that people need to grasp is that, there it is that exceptions allow two unrelated pieces of code to kind of talk to each other. What I mean by that is everything that you do, if statements, else statements, loops, for loops, while loops, functions, all of those things, I describe them as they allow you to kind of move through the code with a pen. Like you could put your pen on the page and you could kind of move through the code and you could tell like a really linear story. You could linearize the running of your program if you wanted to. Whereas exceptions are the first time that you kind of introduce portals or like, wormholes into your program where you're suddenly jumping from one point to another. If you've done courses like 1521 or any other low-level course, you would know these, or even C, you would know these as go-tos, basically jumping from one part of the program to the other. Now, all programming and the execution of programming relies on jumping around to random parts of code, right? The very execution of, a function call and return statements all consist of jumping around. It's just a question of whether that's exposed in the programming language. So languages like, Java and stuff don't have a lot of jumping around, or if they do, people don't use them too much, And I guess that's true for most high-level languages. So that's kind of why exceptions are there. They allow us to gracefully deal with programming anomalies, as opposed to our program just crashing. So the way to think about exceptions are that an exception is like a hot potato in the sense that if a function has a problem, what it does is it creates a hot potato called the exception object, and it just starts throwing it. In particular, it throws it up. It throws it up to the person who called the function. So if you're in function A that was called by function B, and function A has an error, creates a hot potato, throws it up to function B, and that keeps happening until someone's happy to catch that hot potato. And that hot potato is, as I mentioned, called the exception object. And it is an actual object of class type std exception. Std exception is itself a type that you can look up online. It really doesn't have too much exciting about it. It has copy assignment and copy construction by the looks of things. Yeah, it's copy assignment, copy construction. And all it really has is this one particular function called what. And what simply returns a, pointer to a const char, which is another way of saying, a C-style string. And so you call .what, and it gives you a message, because when you construct these things, well, actually, in this case, this is to do with inheritance, but typically when you construct these things, you'll actually attach an error message to it. Don't worry about that whole virtual thing there. We kind of unpack what that means in a later week. But point is, an exception object, think about it as literally a container for a string, because an exception at the end of the day is just a message. It's a message like an error. It's not really more complicated than it sounds. However, what you will see is these other types of errors being thrown that aren't std exception. They're things like std out of range, std bad alloc. And you'll see this exception hierarchy down here, which has these other types like logic error and runtime error, length error, domain error. And in fact, if I take the std out of range error here and I look it up, what you'll see from this is that out of range is a logic error, which itself is an exception. And you'll also see that when you construct that, you can pass in a string as well. So these things do have a string in them, and they have the what function and everything else that's inherited. Now, what's interesting about the inheritance of this is and again, this kind of jumps the gun a bit because we do talk about inheritance more. However, because object-oriented programming is assumed knowledge in the course, basically I can explain it, which is, your exception is your supertype, and a logic error and runtime error are a subtype, and then you have subtypes under that. And the reason we have this is because sometimes you want to say, I'm actually really interested in catching not just an out of range error, but all kinds of logic errors. I want to catch a length error, an invalid argument, and everything else. Or sometimes you just say, I just want to catch any exception that's thrown. And because of this, what you do as a standard practice is that you make sure that things that you write when you write your own exception classes. Because, let's say you think about assignment 2, right? Like you've got a filtered string view, is that, if someone enters into the .at of a filtered string view, something that, read the spec, I'm just talking generally, they enter something that's out of range, well, then you might throw a standard out of range error, because that's what other programmers know to accept. And it means that if someone who's using your library, calls it and it throws an error, they could catch it with an out of range error or a logic error or an exception error. So as a general rule, what we try and make sure we do as developers is have all of our exceptions at some point be inherited, of course, by the exception object, just to keep things nice and standard. Ayush says, theoretically, if we know what exception is, this heart's blocking it, if we know what exception is the code going to throw, why not put validation for that? Often you do, just to be clear. Like, often if someone was writing a program like this one, they wouldn't let the print index ever be called. It's a very simple example to make a point. In reality, a lot of the errors we come across can sometimes be trickier to know or might be undefined. A good example again might be like a network error or a database error, because basically things can go wrong outside of your control. So this example, and I love the way you're thinking about this, can be a little bit misleading, because you think, well, this seems kind of dumb because I just avoid the error ever happening in the first place. It's like, sure, but maybe a better one for you is like an out of memory error. Because every time, and we haven't done this much in the course till next lecture, but every time you malloc something, like imagine mallocing an array of like 10,000 items, how do you actually know there's enough RAM left that's been allocated by the OS to your program? Do you know there's enough? Are you 100% sure? Can you even check that? Probably not, because it breaks out, well, I don't think you can. It breaks out of the abstraction of what you're trying to do. So the only way around it really is to try and do it and let the process come back to you with that hot potato if there's a problem. So yeah, there are some instances, but of course this one in particular you could easily avoid if you want to. So they're exception objects. You usually can include the exception object by hash including exception, or you can include the other ones like runtime error out of range by hash including std except. They're two different ways to do it. So the conceptual structure of exceptions look like this. You have a try, catch, 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 catch. You can catch many times as you want, because sometimes you might be trying something complicated that could throw many different things, like a length error, an out of range error, and you want to be able to handle them differently, handle different exceptions that might be thrown in different ways. Realistically, that rarely happens. The most common one you'll see is this pattern here, which we also showed in the code, which is like you try to do something and then you catch it if there's a problem, and then you do this last element, which is catch ... and what catch ... does is basically a catch-all. Now, in reality, what should happen is that if you have code that catches something like this, right? In theory, that should catch everything. However, in practice, you aren't always necessarily sure if the person who wrote the exception being thrown inherited standard exception. So, this is a good fallback in an absolute, we'd rather handle this than the program crash kind of way. So your kind of two outs are the catch the super type or just do a catch-all. Also, someone asked a question earlier, which is what is that E for? Well, I kind of mentioned that every exception has a what baked into it. So for instance, if I go and run this program again now and make this one, and then I run it and I type in for, you'll see that it has other stuff, but in this case, it just has vector attached to it. Now that what could be anything. That's a common thing as you go and put different, payloads inside your exception object. Depends what exception and what the context is as to what that has. Sometimes you need a lot more information. Sometimes you don't need more information. Sometimes the exception's packed full of it. Sometimes it's not. Really just depends on the circumstances. But yeah, that's the structure of an exception. You can also see that there are some basic conversions that happen, but generally not extensive ones. Like, for instance, if you throw a non-const exception, you can catch a const exception. Because you notice in this particular case, because exceptions are just objects like anything else we've been doing, this is expecting a const exception, but you can pass a non-const one and it will still process it as const for sure. This is another example of multiple catches. In this particular case here, I've tried to, resize the vector, and this one here is me expecting that something goes wrong in terms of, bad alloc. Bad alloc is the general catch for, an exception that runs out of memory, bad allocation of memory. And then here again, I have my fallback in case anything else happens. Rethrowing's another interesting one. Again, it's not super common, but what we have here is we have a program where if you look at the innermost try, we try and throw t, and then we try and catch. Well, so what's interesting about this program is that you would rarely throw the same exception that you're catching in the code, right? And what I mean by that is, like, if you have code here, no one would ever really say, yeah, I'm going to throw a new standard out of range like that, because you are going to catch it straight away. And it's like, that's not really the use case for exceptions. Like in this case, you would just handle it. You would be like, well, I don't need tries and catches and then throwing something. I will just check beforehand, if everything's okay. Typically where exceptions are always seen is when your try calls a function where underneath the layer of abstraction in your code, something happens which may be exceptional, and then it bubbles back up. So when you see these lecture slides here, this lecture slide isn't really meant to be super indicative, because you typically wouldn't throw right before you catch, but it's more just kind of academic to say, well, if you had a try where you threw a type t and then you caught a type t, you could do something and then throw it again. And what the throwing will do, if you put throw back in the catch, if you just put the throw by itself, it will throw the type in the catch, that object, back up to whatever that try catch was within. And again, now typically you wouldn't see this happen in anyone's code where they have 3 nested try loops. Blocks. Typically what you would see is you go back to our early examples with the exceptions where you're catching an exception like an out of range exception. But what you want to do is, you've seen something below you have an exception, and then once you're done handling it, you want to give it to the person above you. Because these lecture examples are so simple, we're not really doing that because you can't go above the main function. People always ask, well, what's the point of these things? And one of the most common ones I point out is logging. Is I still think one of the most common cases I see, because what you can do is you can basically wrap something in a logging. Maybe you've got some capacity where you do something, and what you like to do is that thing might throw. So what you do is you go and catch anything that's of type exception, and you simply do logging on the information, and you throw it again. So you kind of act as a proxy, middle person in this, just grabbing that information on its way through. But so rethrowing, I wouldn't call it super common, but it is possible, and you will see it in some pieces of code. And it does just, again, move from the inside out in that direction. Tim asks, have we discussed L values and R values yet? Have I blanked that lecture? It's a great question. So L values and R values are covered more in the Wednesday lecture. In short, for now, L values typically appear on the left-hand side of an operator, and they typically have a memory address, and R values typically are on the right-hand side, and they typically don't have a memory address. And what I mean by that is this 5 here, it doesn't have a memory address. It's a value. It has value. It's the number 5. It's an int 5, but it doesn't exist in a memory address in the computer, whereas I is an L value, and it does exist in a memory address on a computer. There's a lot more to unpack there, but that's in the next lecture. Some of the lectures got restructured in 23T1 or while I wasn't taking the course, and I get that it makes sense, but I think there's a few oddball things to do with the continuity of stuff. So That would be one of them. So good spot. Eilish also says, when is a non-const exception used? Basically never, but we're kind of going to get to that now, which is about how to catch exceptions. This is really important. So like, I guess a lot of what we're talking about so far is just like standard exception stuff, but in C++, whereas this is quite C++ specific. The most important thing is that you always throw by value and you catch by reference. And what we mean by throw by value is that, because you can throw anything, and I think just to take a quick segue here, you can throw anything you want in C++. As an example, if I really wanted to, right? Like you kind of get the idea where I throw standard out of bounds, right? I make an out of bounds exception. I have to import standard except. We can try that out. Maybe I've missed something. See if it compiles. Definitely wanted I need to make that a new one. I can't remember off the top of my head. Nope. But normally throw those. But main point is that that's along the lines of what will happen in a vector. But you can throw anything. It's kind of one of the weirdest things about C. Oh, is it the other file? Oh, it's this stuff. Was that all the problem? Nope, definitely not. Cool. Okay, got rid of all that code. You can throw anything in C++. I just threw a 1, terminating due to uncaught exception. And I think this is actually a really important thing to point out, is like anything in C, like the idea of an exception in a way is more semantic, you know, because you can throw anything. So like an exception object is just an object that we happen to associate with exceptions. This int is now arguably an exception object because I've thrown it, you know. So anyway, you can throw anything, but the point of that is that every time you throw it, you're typically throwing a whole value. You're not throwing a reference to something, you're not throwing a pointer to something, you're throwing an actual object. And that's typically because you create the object in real time as you're throwing it as well. However, what is really important, as you'll see in the slides, is that we don't catch exceptions by value or by pointer. Now, by pointer makes sense because if we're not throwing things by pointer, we can't catch them by pointer either, right? So what we do want to do instead is, did I say that the wrong way? We don't want to catch them by value and we don't want to catch them by pointer. You know, most of you could probably translate what you've learned previously around values where you're like, well, of course we don't want to capture them by value because we're going to be copying unnecessary data. That is true, but that's actually not the big reason we want to do it. So value bad, pointer bad, reference good. References are good because it's more efficient. Sure, that's what I just said you get. But importantly, there's no slicing problem. And let me just jump ahead here. So the slicing problem is a funny little idea. I know we say we're going to explore it later when we talk about dynamic polymorphism in week 8, in week 7, actually, I think it might be. But I want to kind of highlight it now a little bit more because when we pass things by value, what we haven't really talked about is that, and if you think back to your kind of basic OO knowledge, what you can say, you know, in a course like C++ is you can say that I'm going to create a class called animal. And then you say I'm going to create a class called dog, which is of type animal, like that, right? And if you think about polymorphism, and I know if you haven't done OO stuff for a while, this is just a quick refresher. You can obviously say, you know, dog or like auto D equals, or maybe, you know, dog D, animal A equals new animal, like that. And you can also say dog D equals new dog. However, because of polymorphism, you can also say animal A2 equals dog. This line is really important, right? This is just polymorphism. Polymorphism is the idea that there's a, can't remember the exact term off the top of my head. There's a type that your variable is saying it is, but it's in actual fact a different type. And the reason that this is really important is because in C++, things are very different to Java, right? Because in Java, when you do something like that, right, like you say animal A equals dog, is it new dog? Can't remember in Java. I think it's new dog, like that, right? Like that would be a Java line. What actually happens in reality is that you go and create a whole new dog, right? And then animal is just a pointer to that dog. However, in C++, the problem is that when you have A2 here, A2 is going to be of type animal, and that means that a specific amount of memory needs to be allocated. And again, if you're not sure what I mean, you could say, well, an animal is going to have a private name, right? Standard string name, like this. However, a dog, which inherits the name, is going, or I should call this protected then, I guess. It's also going to have a, or it also might have like a number of legs, right? Because if it's an animal, it might have many legs. A dog has 4 legs, but a dog will also have, say, breed. And what that means is that if you actually look at, an animal, it has a name and num legs, whereas a dog has name, num legs, and breed. This has more memory. So the way C++ works is that if you try and do something like this, right, just being very general here, what it will do if you give it a dog, it is actually, if you make it as an animal, because it needs to allocate a certain amount of memory, and I'm just being quick about this so that it makes sense. What it will do is it will like slice off the parts of that are dog relevant, and it'll just keep the animal part. We call it object slicing because it literally is like that. You've got like a 3-wide dog object, and then you say, oh, I'm going to throw a dog exception, but I'm going to catch an animal. And then the problem is that if an animal is only 2 spaces wide, when it gets caught by the animal, it wipes off the side, and we actually lose some data there. Now, there's not really like a clear error for this necessarily, because if you don't actually call the breed element of the dog, then it's just it might just behave normally. But that's the object slicing problem. Whereas the thing is, when we do these things as references, like that, animal, a reference to animal is A2, sorry, animal reference there, reference to an animal A2 as a dog, this is actually okay, because the way C++ is set up is just like a pointer, which is much more polymorphic, where A2 will just actually point to a dog, essentially. So that's the other reason why we never catch that by value, and we try and catch these things by reference. So this piece of code here is really straightforward piece of code. We've got a giraffe class. We have a constructor. When we construct it, it prints out giraffe constructed. When we destruct it, it prints out giraffe destructed. When we copy construct it, it prints out giraffe copy constructed. And we've got this the main function calls llama. Llama calls zebra. Zebra throws giraffe. So giraffe's our exception object. So because llama threw giraffe, what's going to happen is that exception is thrown, and then we are going to catch giraffe. In this case, we're catching it by value, and then we catch it in llama, and we rethrow it here. And llama was called by main, so we rethrow it here, and it's captured here, and then done this here. And what we're trying to show in this particular example is if I go make by value, it's by value. What's it called? By value. Yeah. Oh, maybe it's already made. Probably already made it before. By value. Why is it not there? That's very weird. Oh, does it still copy it out from before? Very silly. Okay, maybe now. Nope, I gotta remake it, do I? Okay. Whatever. Cool, build that, make by value. Should build that totally fine. And then by value. Okay, now this is really important to see because I not got it up here yet. Yep. We have our giraffe object, makes sense. Line 12 here, we create the giraffe. Sweet. But then what happens is when we throw it, it gets caught on line 19. So we have to copy construct it because we're passing by value, right? And then we print out caught in llama, rethrow. And then when we throw it again, what happens is the giraffe from this catch gets destructed because it goes out of scope because that catch ends, but it then also copy constructs itself down here, and then it says caught in main, and then it destructs that one, and then it finally winds its way back and destructs that one. By contrast, if I just add the two references here, like this, and I run it again, it does significantly less because it's not having to reconstruct the whole object. So we've gone from one construction, or three constructions, down to one just by references. Now, yes, generally it is also good practice to put a const there because there's no real point working with an exception that's mutable. There's no real scenario you'd ever need an exception to be mutable. Things will generally work without the const, but that would be considered bad practice not to have the const there. Now, Tim says a question. Oh yeah, so Ayush says, when is a non-const exception used? Well, the exception you throw, obviously, in summary is non-const, but when you catch it, you're always catching it as const so that no one can modify it because you shouldn't modify it. Tim says, but if it's all nested, doesn't that mean each layer has to make a new object from the reference to throw by value? I'm not too sure what you mean, Tim. I'll think about that. If you think I haven't answered that already, just try and ask it a different way for me and my little brain. Yeah, so all we're saying in this particular code example is you just have to make that simple change to always making sure it's a reference to a const type. And that's really great, really easy from a programming perspective because there's no exceptions, no pun intended. It's like every exception you catch is always reference to const. Now, last few things here, exception safety. Exception safety is really important because what exception safeties refer to is not to an exception object or anything like that. It actually more refers to a function. Every function has a level of exception safety because when you call a function, there are certain expectations around what exception-y things might or might not happen. The first type of function you can have is one that is called to have a strong exception safety. Sometimes we call this as I think like exception guarantee, no throw guarantee. I think these are also called no throw guarantee, which is basically where it says if I call this function, I think I missed one. Did I? Yeah, I did. Sorry, I was like, I'm pretty sure the first one's not called strong. I was tripping myself up. I pressed down before. Sorry. So no throw guarantee is the first one. Strong exception is the second one. That makes a lot more sense. But these are the four, right? So we have our no throws, strong exception safety, weak exception safety, and no exception safety. The no throw ones are ones where what happens is you call a function, but it may throw an exception inside that function, or something it calls will throw an exception, but it is always handled. So it is a true like exception abstraction where it says you calling this function will never throw an exception. That's why we call it a no-throw guarantee, because it's not saying that exceptions will never be thrown. It's more just like if they're ever thrown, you'll never hear about it. You never have to worry about it. It's not a problem. It just happens, and I promise you'll call me, and everything will just be fine. You know, like a true guardian, it looks after things. Examples might be closing files, freeing memory, creating trivial objects made on the stack, like when you create a new int or a standard string, it's pretty much I don't know, I can't remember what it is, or like calling dot size on a vector, for instance, will never throw. So those things have what we call no throw guarantees. When we create functions ourselves that we know are never going to throw exceptions, we will typically mark them, and again, this is mostly semantic, with a no except. You might have seen this around in code at some point, but this no except, when you mark a function with it, and you typically will do it in like the .h file, it's where the functions are defined, declared, I guess, is you'll put it there. Now, this doesn't actually stop functions from throwing an exception. And this is really important because it's a little different to say const, because const is a signifier to a programmer about what the intent of this particular, property is. But no except, this keyword, unlike const, doesn't actually have controls. You can mark a function if you want. You can write a function, mark it as no except, and still throw an exception, and just piss off the people who are using your function. So it is purely a signal to people, not a protection. But it's one that's quite common because people like to know when your function will not throw an exception. Because if you're a programmer who's working on an important piece of code, right, then you need to make sure that every function you ever call, vector.size, vector.pushback, every single one, you got to read the docs and see, may this throw an exception or may it not? Because if it can, you will always put it in a try catch. And people don't want to add try catches all the way through their code if they don't have to. So this is a great way to say you don't actually have to use that try catch. Strong exception safety is the second one. Sometimes we refer to this as commit or rollback semantics. What this is saying is that you can call this function and it will potentially fail. It will throw an exception, but there are no side effects to calling it. I like to jump to the next slide because I think this kind of shows it, which is like, if you're writing a function that you want to have strong exception safety, that's not no throw safety. That's saying that I may throw an exception, but it has strong safety. Any operations that you basically reverse anything that happens. So good examples, like let's say that you're doing a resize, right, for a vector, and you start mallocing memory to resize it. But then after you've done that, there's an error. What you do is you unmalloc, or you free that memory back up, so that when someone kind of like calls you and there's a problem, they know that everything's been cleaned up. I use that word side effect very intentionally before because we don't ever have side effects for strong exception safety. This is kind of telling you how to write it, as you always try and do your potentially throwing stuff before your irreversible mutations, because obviously, like if you're writing a function, there might be something you do that you can't undo, like closing a file or pushing to a vector or removing an item, so you always want to make sure that when this is the implementing it, the strong exception safety, you do the things that may cause errors first, and then once you're like, yep, we've gone through everything that may cause errors, then you start to do the irreversible things, because obviously if you did something irreversible and then there's a problem and you have to abort, that's terrible. But yeah, many things have strong exception safety. Most things can be no throw guarantee. Things that can't be are like things that actually throw exceptions will usually have this. And then you kind of get into the tail end, which is like you've got like basic exception safety, weak exception safety, I think I've seen it called sometimes, or no leak guarantee. What this is saying is that if you call me and I fail, there may be side effects, right? Like as in something may have changed, the data may be corrupted, things might not be where you left them originally. It's not idempotent, but it guarantees you that there's going to be no memory leak. So basically says if we malloced anything as part of this operation and then something went wrong, we made sure we unmalloced it. So you could call this a million times, and whilst your data might get corrupted and invariants might not be preserved, there's no leakage. There'll be no memory leaking at all. Yeah, that's that one. And then no exception safety. There's no guarantees for this one. Generally, no one really writes this. Obviously, we talk about it because it's like theoretical. Like it's possible, right? Like someone can write a function that has side effects and leaks memory, and we would say that has no exception safety, but it's not really like a thing that exists. Like you won't find functions in the STL, set of containers that have like no exception safety. It's typically strong exception safety or no throw guarantees, or maybe like a weak exception or basic exception safety. So they're the main different areas of exceptions that are relevant here. Just having a look through some questions. Tim says the compiler doesn't at least check if all the caller functions are also marked no except. I don't believe so. Not that I know of. Maybe like with a warnings flag or something it might be possible, but I don't know. I haven't seen it myself. Yeah, for sure. Just looping back to Tim's question. Tim was talking about the llama one. Tim says, in this example, isn't the throw in llama not by value? I assume you're talking about the reference one, right? Or are you talking about... Sorry, I changed the value one. Should change that back by reference. Otherwise, wouldn't it need to construct another giraffe from the reference that it caught? How can it catch by value and throw by reference? I don't think it does, unless I'm misunderstanding you here, but yeah, like in this case, it doesn't throw by value. It throws G, but G is a reference too. So if it catches it, like with anything with references, right? Like if you have a function that has a parameter as a reference and it returns that same parameter, it's not really returning by value. It's also returning. I mean, I guess it's hard because we kind of talked about it a bit. Like if you have a function int stuff that takes an int a, and int's a reference here, and then you say a plus equals 1, and then you say return a. The return type here kind of dictates what happens, and I think this is kind of an important thing because like whether something's captured by reference or values typically on the receiver end, right? Because this function here, a will be passed by value, it'll be copied out as it in its current state, I believe, unless there's an error. Maybe there's an error, I'm not sure. But I mean the same kind of applies for parameters here, whereas this one's kind of by reference. And similarly here, if we kind of got rid of this, then yeah, it would come into zebra by reference, right? So nothing needs to be copied. But when we throw that reference, because what's catching it, let's see if it works. Like I don't need to sit here being theoretical. We can just do it by reference. Yeah, that works fine. And then it should print out, 5.1 by reference. Should print out 2 copies. Constructed, copy, constructed. Yeah, so same thing. It's like the power's by the receiver. So if the receiver says it's a reference or the receiver says it's value, that's what the compiler does with that. I hope that makes sense. It contradicts the point to always throw by value, maybe only relevant in the originating throw. Sorry, I understand what you mean. Yeah, I mean, I get it. So your kind of question comes from this like, sorry, where is it? Yeah, it's this one. Throw by value, catch by const reference. Yeah, I mean, maybe that's more a conceptual point because, I mean, if you think about it, it's like you can't really throw by reference or throw by value, right? Like you can only throw a name. And what I mean by that is if I go back to my simple example, you can never return, like, you're just returning a, right? If it's an int or an int reference, it's just a. So like the throw by value, yeah, you could argue is like redundant because like you're always just throwing something. It just depends on how something's caught for sure. It's probably more just there, I imagine, to kind of help people understand that, when you have a problem originally, not a rethrow, maybe to make more sense if it said always initially throw by value, the thing you're creating is a real thing, and then forever on that's just being like referenced from there. So I like that you're digging into that level and trying to make sense of that. That's good. Yeah, cool. Excellent. And then honestly, it's pretty straightforward tonight. Last thing for tonight is just this slide here, exceptions and catch to. So I added this for this term, or recently. No, I think I added anyway. I cleaned this up at least for this term because in assignment, is there exceptions in assignment too? Let me assignment 2. There used to be. I don't think there is, because I don't think we ask you. I didn't think there was. There used to be though, I think. Unless I'm missing something. I was pretty sure there's not anymore because I didn't see any. But now it's mostly for I'll come back to those questions. Yeah, I guess this is mostly for assignment 3 because there are actually exceptions in assignment 3 in a fair bit of detail. But basically the point is like with catch 2, and again, we encourage you to go and look up specific examples and look up, like, again, this is a great example of GPTs like Gemini and Chat GPT, as you can just punch in like, hey, give me an example of using check no throw. But basically, you give an expression to check no throw, like a function call. If you think it's not gonna, if you expect it not to throw and that's what you're testing, you give it to check throws if you're expecting it to throw. You give it to check throws as if you're expecting it to throw a specific type, like standard exception or standard out of bounds or something like that. And then these ones are if you're trying to check it's throwing with like a particular message, attached to it. Generally speaking, as you go further down the list, it's not as critical. But these are the different ways that you could kind of do it. At a minimum, you'd kind of want to get comfortable with these like, throws ones or throws types ones. But again, you don't really need to do that as far as I can tell in assignment 2. I'll double check that. I mean, I know that sounds a little bit like weak, like I'm not too sure, but like I'm 90% sure it's not. I, again, just didn't write this assignment in the end. I'll just go double check our auto marks aren't there. But essentially the extent of exceptions in this assignment is you marking things as no except. And I think just to be clear, when I say there's no exceptions in this assignment, what I'm really saying is that I don't think that we expect you to throw exceptions. You're like create exceptions and then throw them, because obviously if you're using something and there's an exception thrown in your function, that's fine. Like your functions can throw exceptions. We just don't specify anywhere that you have to create your own types of exceptions and throw them with specific error messages. Because obviously if you were say like, if you like did a .at on a vector and it was out of bounds or something, of course, because there was a vector in your function, you called it, not that's a bad example because it wouldn't happen, but there's going to be an exception, so your function might do that, which is really kind of, I guess, like if you look at the 2.12, we're saying that any functions that have a no throw guarantee need to be, or should have a no throw guarantee, need to be marked as no except. And other things can, shouldn't be marked as no except. So when it comes to the marking of your assignment, it's actually your tutor that will go and look at how you've interacted with the exceptions, and whether they're in the right place or not, basically. Metagross says it's only, yes, tonight's shorter. Magic Steve says, do we have any lecture mainly focused on closures? Or do you recommend any tutorials about that online? I don't know. Send me an email if you want me to answer that. Otherwise, put it on the forum. But I'm sure we can find you something. I don't think we have a lecture that spends much time focusing on that specifically in a great deal of depth. So just, again, start that question with either the forum or email me, which should be the main one. Do we have any other questions about exceptions before we wrap up this particular lecture? I'd love to hear them now if you do. I'll give you 30 seconds for the chat to catch up, because we know that takes some time sometimes. Running on battery. It's fine. It's not a big problem. I at least, I've had Windows most of my life. I at least like that MacBooks seem to run down to 1% before they die. Whereas Windows have that kind of funny thing where they shut off at 8, which I'm not a big obsessor about Macs being that much more intuitive, but I do like little things like that. You'd think you can use your laptop till it goes to 1%, not like at 8 on Windows laptops, which is always quite funny. But yeah, okay. Well, that's all. Well, again, a short, easy lecture tonight. Again, honestly, a lot of the rest of the term's pretty light on content in terms of heavy lectures. So we'll have a pretty cruisy, pretty cruisy time for the rest of the term. But thank you for coming. I'll see you on Wednesday. I'll see you in the physics theatre. We'll have a lot of fun together talking about memory, L values and R values. And we'll chat soon. Thanks, everyone.